is what we've finally been waiting for in determinate forms. In L'Hopital's rule. And this is going to take care of a lot of the limits that we've been doing algebraic manipulation. We can now do it through a much simpler process. Like all those trig limits we talked about, you had one on the exam, which most of you fumbled, right? We're not going to knock that thing out like nothing, right, with L'Hopital's rule. And, I don't know how you want to spell it, whatever. I'm just going to start with examples from your textbook. There are three main types that we'll discuss. First of all, I guess I should say this. Indeterminate form, the main one is an indeterminate quotient. I'm spelling that wrong. Indeterminate. I'm spelling like determinate, like it's like it's some kind of anti-linear algebra thing. Hold on a second. Indeterminate. Indeterminate.
Is it too much code?
So it is it?
Too much code compared?
Too little, I think.
You could smell it outside.
If I had Code Comparo, man, that'd be rocking right now. Indeterminate quotient is the most important one. And anything that is not an indeterminate quotient, which we'll discuss momentarily, we are going to change to an indeterminate quotient. Because indeterminate quotients are what L'Hopital's rule applies to. Okay? An indeterminate quotient is this, basically. It is limit as x goes to a of f of x over g of x, where the limit of f of x as x goes to a equals limit g of x as x goes to a equals 0. That's one type of indeterminate form. This is the 0, 0 case. I'm just writing out more formally than we did at the very beginning. But it's the 0, 0 case we talked about when we took derivatives using limits and the other basic limit cases. Okay? Or lim f of x as x goes to a is either infinity, which I guess is the same as the other one. Doesn't matter, so I'll try the same thing again. Lim g of x, as long as they're both infinities, that's going to be indeterminate form. So the basic cases, the way you usually write it is just this. You just shorthand it, 0 to 0 case, or infinity over infinity case. Those are our two basic cases. Where here, the plus minus is irrelevant, doesn't matter which one it is. Doesn't matter if it's positive or negative, negative or positive, 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 negative or negative. For the infinities, it doesn't matter. All right? That's an indeterminate quotient. And that is the scenario in which L'Hopital's rule applies. So now what's L'Hopital's rule? If you have a case like that, you have an indeterminate quotient, then L'Hopital's rule, too many apostrophes.
Does that mean hospital?
Yeah.
I mean, that's the way some people spell it. Some people just skip the S so that people don't say L'Hospital's rule. That's not how you pronounce his name.
Oh.
But some books have an S, some books do not have an S. Right? And I'll refer you to Serrati back there. Again, he will tell you the correct pronunciation for that name.
Is that where the word hospital came
No.
from?
What's that?
It's a good guess.
It is the same word. In French, it's the same word.
Hospital.
In English, right, but it doesn't cover his name. You know what I'm saying? His name has to be the same as the word for hospital.
This man right here invented the hospital.
No, he didn't.
No, he was just
This is how they figure out what a blood transfusion is.
It's like the hospitalers. Remember the hospitalers? The hospitalers?
That sounds like a country.
Yeah, something like that. All right, anyway, so L'Hopital's rule is if you have this case, right? If you have the indeterminate quotient, right, that I've just described. Indeterminate quotient. You have that, then that indeterminate quotient, the limit as x approaches a of f of x over g of x, given that it's a 0 to 0 or infinity over infinity case, is that case. If you have that case, then this limit is the exact same thing. I'm going to put a little h over this, meaning it's equivalent through L'Hopital's rule. Okay, that's the way some books write it. So I'll try to remember to do that. It is equal to the exact same limit as x approaches a, but instead of the original functions, it is of their derivatives. Okay? So f prime x over g prime x.
What is the h in that?
It means it's equivalent through L'Hopital's rule. That's how you get from this to here. It's saying they're equal. They're the same thanks to L'Hopital.
Wait, so explain it again?
So if you have, I'll just write an example. So let's say you have lim as x goes to infinity. We have a very simple case. Let's say it's 2x minus 8 over 3x plus 4. You have that case, okay? We should all know the answer immediately without L'Hopital's rule from our discussion of rational functions and their horizontal asymptotes from way back like a week and a half ago or something. What do you say? 2/3. The answer is 2/3. The answer is 2/3 because the degree of top and bottom is the same, right? So when it's the same and you have a limit as x goes, you have a limit at infinity, then the answer is the ratio of the coefficients, 2/3.
You're finding the horizontal asymptote when you do
We are.
this?
We just found the horizontal asymptote of this rational function. That's true. Okay? We found the end behavior of this rational function. So now, to L'Hopital's rule, though, first I check. As x goes to infinity, is this an indeterminate quotient? Is it a 0 over 0 or an infinity over infinity case? The answer is yes. It's infinity over infinity. The top is certainly heading towards infinity, and the bottom is heading towards infinity. So since it's infinity over infinity case, I can apply L'Hopital's rule, which says this should be equivalent to the limit as x goes towards infinity of their respective derivatives. So the derivative is 2, and the derivative is 3. Right? The derivative of 2x minus 8 is 2. The derivative of 3x plus 4 is 3. So what is the limit of 2/3 as x goes to infinity? 2/3. It's a constant.
And so, I guess my question is, so what are we trying to find with this?
Limits.
The limits?
Try to find the limits. This is another way to find limits.
Oh, okay.
So instead of finding the limits and making some algebraic trick or something, or knowing certain rules, what we can do is we can take the derivative of the top, take the derivative of the bottom, and then reapply the limit and see if we can analyze it more easily then. Okay? Take another quick example. Show you the power of this thing. Let's say we have something slightly different. 4x squared minus 3x plus 2 over 8x squared minus 5x plus 7. Again, from what we discussed earlier, you should know the answer immediately. What is it? 4x, which is a half, correct. Let's say you didn't know those rules. Can you apply L'Hopital's rule right now? Yes. The top is heading towards infinity, the bottom is heading towards infinity. So I should be able to take the derivatives of top and bottom separately. You're not doing quotient rules here, right? For those of you who've never seen this before, you're not doing quotient rule. You're taking separate derivatives. So this should be the same as, again, L'Hopital's rule. Should be the same as, let x goes towards infinity of 8x minus 3 over 16x minus 5. Agreed? So do we have our answer now? No, we don't have our answer yet.